So welcome everyone.
Good morning.
Good morning. It's a privilege to meet all of you who are so excited to be here. Where did she go from? Emilia is going to accompany us. She's a new intern with us and hopefully training her to do some of these tours for our younger crowd as we go forward. So, without much ado, my name is Girish Chachad. I've been working here for a long time, and that tells you I love working here. As I said, I had heart surgery last year, and I'm still here, standing and running. The only difference is I'll be taking the elevator up instead of walking up the stairs. Otherwise, everything else remains. So, welcome aboard, and our main tour today will encompass the sim labs, which is the simulation laboratories. And we basically are spread out in 3 different buildings. This being one, that's the VMS, the vertical motion simulator or system. This one allows us to do different types of vehicles. So if you look at the showcase behind you, hey, how can we do a fighter and an airship and a shuttle or helicopter in the same simulator? We can do that because we have 5 cabs, which are these white boxes you can see up here. That's your cockpit in the inside. I'm sorry, I was trying to get out of your way there. So,
I think you're probably supposed to be.
what's that?
You're supposed to be in the shot.
The cockpit, the insides, as you'll see upstairs, are different for different vehicles. And you can configure them any way you want. So if you come in as a researcher and you want to look at, say, a new vehicle that you are developing or you're working for somebody, we can configure it to your needs. So the 5 cabs allow us to switch around. So one day, like the shuttle cab is upstairs right now. Once the shuttle simulation is over, Friday we can swap them for the next sim that is getting ready downstairs. Monday morning, we do a quick check for a couple of hours, and we are ready to start the new simulation. Okay. So, we have streamlined that process. We've been doing this since '81 on this simulator. We had another one before this called Advanced Flight Simulator, FSAA. This one has more vertical travel. Okay, so what are we doing? Overall, we're trying to simulate aircraft or vehicles, any vehicles. We've done others before. So before I start getting too deep, let me get back to the initial idea of what the 3 facilities. So VMS is one, CVSRF is another one which we will go by but not in, right? Okay. FFC is the Future Flight Central, where we can simulate an airport tower. It has a 360-degree viewing capability. So it's a basically visual capability. You can use it for anything you want. You want to do a party, you can do a party with things going on around it. But obviously we are using taxpayers' money, so we won't do party. However, one can use it for space exploration. So when you go there, we'll have a special treat for you guys. You get to see the Mars terrain as recorded by the rovers. You can do underwater stuff. So if you have some kind of exploratory vehicle going underwater, as it's seeing things, one can be displaying the same images on land, and people who are doing the research who could not go, I mean obviously your vehicle might be limited in how many people can go, but the researchers are on land. They can be in the lab experiencing everything just like the researchers who are in the vehicle. So, 3 facilities together can be linked and networked to give you a real powerful simulation capability. And I'll elaborate on that as we go forward. So, CVSRF, by the way, has 2 different hexapod systems. So, if you look at this motion system, it has a different mechanism to give you the motion. Those will have a cab like this, and under it there are 6 legs. That's why they're called hexapods. So the 6 legs, by expanding or contracting, give you the motion in different directions and the rotation and so forth. The only difference is when you have 6 legs, you go, say, maximum in this direction, you're limited in how much you can go up and down because once the legs are extended fully, you can't do that much more. This one, you can go all the way to the left, all the way up, so they're independent. Okay, so you can still achieve maximum limits on each travel axis. Okay, so I'm trying to stay out of being too technical. I want you guys to leave with a few points that will, help you see where we come in terms of relevance to what NASA does, relevance to what the country needs, how it affects us overall. And second, lower level, why do we simulate? I tell everybody, mainly there are 2 reasons. One is safety, second, economics. When the children are here, I usually tell them, hey, forget everything I said, remember those 2 things. So, they are relevant. If you look at it, when Intel does its little chip and puts it in Celeron or the dual core, puts the chip in, they are taking on a lot of risk, right?
Yeah.
So they better simulate that baby many, many times before they put it out there. Why? Once you put it in thousands and millions of computers, could catch fire, could do the wrong computation and suck money out, even 1 cent from everybody's bank account, and give somebody millions of dollars, be open for liability suits, right? So, you can go into the different issues. So, it is very important for them to simulate them to be safe. And look at the repercussions, right? If the thing does fail, or these millions of chips fail, and for them to do a recall and refurbish the computer is going to cost them a lot of money. Okay. So, simpler analogy is, hey, you're going to get married, don't you want to know what your marriage is going to be like? Similar. Okay. So, I normally didn't use the marriage analogy because people thought, I just used it a couple of weeks ago and somebody said, hey, that makes sense. So I'll use it again. So this is perfect. Okay, you have a vehicle like the space shuttle. It costs millions of dollars, not only to send up each time, but to get the whole system ready to go. It's a lot of trouble. Okay. So, what do? We gave the shuttle a couple of things. One is engineering, to help them validate what their vehicle could do, validate changes to their systems. Okay, so most of you have seen pictures of the shuttle landing with the drag chute opening when it's doing that. The drag chute was not part of the original system. It was added later on to help them arrest their speed a little quicker so that they could land on shorter runways if they had to. So you can always go look up the details of the space shuttle. I'm not the expert. By the way, when I give tours, people expect me to know everything about NASA. I don't. I know, what's it, this much. NASA is huge. And the amount of stuff there is, I learn something new every day, even now. So like today, we were talking a little bit about Yelp. I'm trying to find out what I could do to give you guys a better tour. So, space shuttle, drag chute wasn't part of the original system. So before they actually implemented it on the system, they tested it here. The astronauts were able to fly it, comment on it, give their approval in a way, because they're going to fly it. Okay. So, by the way, any pilots in here? Okay. Good. So pilots normally do not want automated systems. Okay? Right? They want, why are they become a pilot? Because they want to enjoy that thrill, okay, to fly. So you ask the astronauts, they have a auto-land system, but I believe it was used only once because they wanted, they implemented it, so they were, they meaning the engineers wanted to make sure it worked. Pilots obviously did not want to make it work because they say, hey, we go up there once in a lifetime. I want to fly this thing all the way down. So there's always that. So you have technology, and then you have the human side. Okay? There's a mix. There's a lot of interactions. So I'm starting to get into another domain. However, the point being, pilots want to fly. So when you take a shuttle type of vehicle, how much we gave them in terms of engineering, very valid over the last 30 years. The first time on this system was the shuttle, by the way, in '81. Last year we celebrated our 30th anniversary. I have some handouts I'll give you when you leave. So let me get everything back down into how this system works, how we can make the simulation system fly and make it valuable for our customers. So who are our customers? NASA, obviously, so other parts of NASA, DoD, other government agencies, so NTSB can be one. So any accident investigation, sometimes they have been here to check some things out. It's an interesting thing, once I see some accident happen and the aircraft went like this, all the pilot had to do was pull the stick back. Great. Did he know what was back at that point when he's going all the way up? Humans get disoriented. So that's where motion comes in. Motion helps you out to actually feel the reality of what's going on. Okay? So what are we trying to do? We are giving the pilot the full experience of flight. So VMS is structured in such a way that before you go to a test flight, this is the next best thing. Okay. And probably the safest thing you can experience before you go. Okay, so researcher from NASA or Lockheed or NTSB comes in and says, I want to simulate this particular aircraft. What we need to do is get a model from them, or we develop one for them, implement that on a computer system. Computer system basically is the nucleus. Okay, so the pilot is flying, puts in the stick, controls or rudder or whatever he or she does. So here's a computer model. The inputs from the pilot come in. What comes out of the model is sticks. So if the pilot pulls back from the stick, the aircraft is going to pitch up. Right? Keeps pulling back. So the computer model is basically computing the states every 5 to 10 milliseconds, which is 1,000 milliseconds. And it's, these days it's not difficult because the computers are so fast. In '84, my first sim was the Harrier. My computer I used was so, what should I say, rudimentary compared to today that the RAM was about 64K. Okay. So his earpiece probably has more than that. Okay. We have to be careful how to program and all that stuff. So paradigms change, things change, and we have to keep up with them. So what I was trying to say is there are things to do with the computer that we have to worry about. So when you come to us, I'm not an expert on the shuttle, or we are not an expert on one particular bit, but we are experts on simulation. So if you want to simulate something, we know the principles that will take your aircraft, package it into a system here, so when the pilot flies, he or she feels like it's your aircraft. Okay. So the other point being, when we are flying on here, we are evaluating the vehicle in this particular system. In the other CVSRF simulator, it's more human factors, meaning we are evaluating how the person performs under certain conditions or changes. Okay. But does that mean we can't do training here, or we cannot do human factors? No. I'm telling you, majority of it is vehicle evaluation here, human factors there. Okay, so I want you guys to see the real thing upstairs. So another couple minutes. This whole beam and above weighs about 150,000 pounds. It's pretty heavy. So some of you who are mechanically inclined, engineering-wise, you'll realize that to go up, it's going to take you a lot of effort. It's going to be sluggish in a way. That means if your pilot's flying up, he's going to feel like, oh, it's not climbing that fast.
Yeah.
But going down, it's going to go down pretty fast and easy. However, that's not what we want to give the pilot. We want the pilot to feel like he's flying an airplane. So one thing that was done was those two columns you see, the blue ones, those are actually going into the ground, and they have the nitrogen system. Think of it as a jacket. They act like pistons. So at any given moment when you're operating, this whole beam is floating. So technically, if you went and push it with the finger, you should be able to move it because it's floating. Okay? Bottom line, the system gives you the same frequency response in either direction. That way, the pilot doesn't have to get the wrong impression about the aircraft. So, just one point I'm trying to make. Another point, okay, so travel-wise, this beam allows you to go 40 feet horizontally, 60 feet vertically. This slice here, the platform, goes in and out about 8 feet. And then the rotational degrees of freedom are about plus minus 18 to 24 degrees. Bottom line, it has a lot of travel compared to most other systems that are operating in the world today. It's probably the largest volume operations today that we know of. Other couple of neat things. So when you say simulation technology, what does that mean? Our goal is simple. We want the user to feel like he or she is flying the real aircraft when they're in there. So everything that's needed to give that impression or feeling, so the motion gives that feeling. The visuals, as you're flying, you've seen video games. So you scream, but what we do, actually we have to do it better because we want them to feel it's real. So visual system, the audio, and then there's a force field. When you're flying, just like your car, when you're turning all the way, these days you have power systems to assist you, but when you're turning, in the olden times, the mechanical system, as you go towards the end, it's harder to turn, okay? And that's something that pilots use as a cue. When they're pulling on the stick, they want to know when they're getting close, not when they find out it's the end. So you want to know, okay, I'm running out of control authority, because it's gone. Or, it's getting harder. So the stick inputs, it's called force field, is very important. So all those things, so you as a pilot, if you were to fly in here, we can simulate the Cessna for you if you want.
Okay.
And ready? So you'll feel like you're really flying the Cessna. And we want the pilots to feel like. Okay. So I mentioned 4 cues, motion being one, visual, audio, and force field. So those 4 are very important. In the home video game, you get the 3 except for the motion. These days I know there are some seat shaker type things that you can buy to get some of it. So, trying to get deep again. So let me get out of that. Couple of neat tricks that we do. Okay, if you imagine, at some point you're going to run out of travel, right? So if you're doing a helicopter, you go all the way on one side, you're stuck. Then if I want to simulate more acceleration, I'm out of luck, right? There's no more room. Or going up, same thing. So we can do certain things to give the user the feeling of continued acceleration. How can we do that? Simple. When you drive a car and you accelerate, what do you feel?
Back
You feel that extra pressure on the back. So if I can give you that extra pressure, continue to give it to you for a while, you feel like you're still accelerating. Okay, because you're in the cab. So if I tilt the cab with your weight on the back, my visual is still up there. So as far as I can tell, my visual is still in line with the horizon is still in line with my body. But I have that extra pressure on my back, makes me feel like I'm still accelerating. So just one, and you can extrapolate that to the different axes. Another thing we can do is, because to avoid running out of travel, is as it's moving around, the tendency is always to bring it to a center point. That way, you have the maximum volume to go to the next required instant. Okay. So, and it's done at such a low rate that the body cannot perceive it. It's about 0.3 feet per second cubed. So it's called jerk. It's beyond acceleration. And you do it at that small rate, the body won't feel it. So you won't realize it's happening to you. So if you're flying level flight and nothing's happening, you're just sitting stationary. Slowly the cap's coming back to the center, always. Okay, that's one. And then another last point is the cap can be rotated this way, by 90 degrees. So right now the door's in the back, that means the pilot will be facing that way. Visuals are in the front. So if you were to fly helicopter, transport aircraft or shuttle, where the lateral motion is more important, because it's not going to do a fighter type of motion forward or helicopter where it can go fast and slow down. In that case, this orientation works. For helicopters and fighters, you might want to orient this way. That way you have more travel along the longitudinal direction. So that's another new thing. All right. Any questions? I'm talking too much. Hey. Okay. You want to go upstairs?
Oh my God! Holy moly! That would be scary to me. Holy crap!
Oh, there's a picture too.
That moves a lot quicker than I thought it would.
Yeah.
Holy shit!
Wow.
It's so close. I am a terrible piloter.
Make sure to
That guy loves it, so he gets to go. Whoa!
Just to make people sick.
So, if the aircraft itself is capable of making them safe, yes, it will make them safe. However, the key scientifically is we have to make sure that everything matches.
Right.
So what you see and what you feel has to match. Okay? If you're doing a treadmill at home and in front of you, you're watching TV and say the picture is going the other way, what's going to happen? You're going to get sick. So that's an extreme case of reverse, right? You're walking forward and then the picture is going the other way. So we have to make sure. So in this case, I talked about milliseconds. So there are milliseconds of delay between the computer spitting out its output and it going to the visual, going to the motion and all these things. So ideally, say if you saw something and then a second later you felt it move, probably you're going to get sick. You want those to match. So it's a lot of times if there is, so engineering wise, if you look at, there is going to be some delay in what happens. So let's say you have a 100-millisecond delay on the visual, and then motion says 300, for example. Okay? Milliseconds, not seconds. One would like to balance it so that they're both matching. It's not good to have one really fast and one slow. Okay? So those are engineering decisions. So things like that have to be decided.
I'm just curious if you have motion sickness or just
Me?
in general.
No,
Just
I
you
was
don't
fine.
You don't
But
make
today I don't know because since my surgery I haven't gone in.
Okay. So let's not do that. Let's not trust that.
So we'll get to see the cap. I know we have. So step in and move it. Yeah, that's right.
Hold on.
Okay, that's good. All right. So, well, this is the shuttle cab, as you can see. This is what we use for training and engineering studies for the shuttle people. The astronauts came in here about twice a year to practice. So imagine the value to them. They
Look at on
can't.
the floor. Look at the picture. This it's like
Yeah, so
you're
you
moving.
can see that it
On the
is
runway.
running right now. It's
Yeah.
landing. Actually, can you put the light above you? Yes. There you go. So if you
Oh
watch
my
the visuals, what do you feel? Feel like you're moving?
seeing
right?
it, yeah.
The
Oh,
visuals are
yeah.
slightly different. They're not just
I
like
hope we don't
a
crash.
regular monitor by itself. Okay. The image is collimated. Exactly. You can look it up.
Wow.
So the astronauts have to be trained to land on the regular sites, airport sites, as well as the abort landing sites. I keep forgetting the program is over, but I still say it in the present tense. 21 runway sites. Can one take the shuttle to each one of those and land them for each of the astronauts? This works out a perfect solution for them to practice if they ever have the need to land at the Spain runway. Guess what? You can say, hey, I flew in the simulator, I know exactly what to do, I know what to expect, there's a better confidence level for you to work. Okay? Alright guys. Alright, now I'll let you see you want to see the whole plan?
Yeah.
Let you see it.
Feel yourself sinking.
No, there's the dumb button. Girish, we're meeting to SFO right now.
Right. So Kennedy, White Sands, and Edwards. Those are none of the abort landing sites were used, but they are there. Sure. Well, so a couple of things to know. I mean, aircrafts have a thing like a glass plate called HUD, head-up display. Basically, if you look from the side, you'll see green symbology on it. The point being, the pilot has to be very agile. He or she is flying, he doesn't even want to look down to see what's my airspeed at. If you look back up, you might be in trouble. So you can look straight through here, watch the outside, at the same time know what your airspeed is, know what your altitude is, all the key parameters are visible. Right? Alright, you want to send the next group link, please? I wanted you to see where we do a lot of the work. Okay, so the cabs get set up in here, we check them out, and then when they're ready, put them on one of these carts, goes out that door, goes around the building, there's another roll-up door in the big building you saw, comes in and they put it on the beam. So that's simply put what we need to do. But obviously there's a lot of work to get from something like this to a completed cab that you saw upstairs. Okay? So this one is a fighter cab. You can see how the skeleton is, how we have to add things on, get everything working. It has to be safe too. I mean, our simulator gets motion rated every time. That's why we have certain rules. Kids have to be 18 to get in there. We don't let them fly motion unless they're 18. There are rules. Okay? When we do research, there have to be certain protocols that are followed. You know, about using animals, no animals. There's so many things. So in here, all we do is human research. Okay.